Hi. So in dicex, there are verilog files, and to really do the project that is in dicex, you need to learn to use the verilog files. Today I want to give an example using the counter. If we open, let's see, pro dicex, sim, verilog, and there will now be a counter.sv, which includes a small counter. So in this counter file, we have our output, which is the out, which has a parameterizable width. In this case, the width is 8-bit. So we go from 7 to 0 with the MSB up first. We have an input, which is a clock. And we have an input that is the reset. Actually, this line we don't need. Inside we'll have an always FF, and that gives us sequential logic, where if we get a posage on a reset, we will reset the output, and if we don't have that but just have a clock, then we will increment the output by 1. It's a very simple counter. To be able to test this counter, we need a test bench. So let me open them both at the same time. So the counter on top, the test bench on the bottom. Let's use a timescale of 1 nanosecond and the module test, which is our test bench. In this test bench, we'll set up the reset signal and the clock signal. Now, the clock will generate by an always statement where we assign the clock value after 5 nanoseconds. So every 5 nanoseconds, it will toggle. Then we have our count variable, and we instantiate the counter, give it an instance name, C1, and we have the output connected to count, we have the clock connected to clock, and reset connected to reset. To make something happen in the verilog file, we start by creating a dump file, the counter VCD, which is I think it's called the value change dump, where we'll add all the variables inside this module called test. When we start this simulation, we'll first reset, assign reset to 1, and then assign it to 0, and then we'll stop after 50. Well, actually, this will be 10 clock cycles. Okay. To run this, we start dicex. Let's see, let's clear that. Actually, it starts cicada. So this starts the Linux box in Docker. And I can go into cdsim, verilog, counter, sv. And we can have a look at the files. So here we have the counter file, we have the counter test bench, and there's a few other files that we'll get into. But let's start by looking at the make file. So the make file I've written to be able to run verilog for me. So if I type make run, it will run this first command, which will compile the verilog file, and counter fl is just the list of the verilog files I want iverilog to compile. After it's been compiled, VPP will run it. So make run will run this verilog simulation, and that's pretty quick. To be able to view the files, you need something that can read the value changed up, and one program that does that is GTK Wave. Now I've opened this already, but you can just go to File, Open New Tab, and then find your counter value changed up, which will give you the test module, and we can put in the signals. Now let me zoom in a bit. There we go. So when we look at the signals in this value change dump, let's put reset on top, clock, and let's plot this one in decimal, and we can zoom out. So here we can see at 10 nanoseconds, so if I open the test bench, Actually, you can't see that right now. But at 10 nanoseconds, we set the reset high, and then 10 nanoseconds later, we set it low. And that resets the counter value. As soon as the reset goes low, at every single rising edge of the clock, we will increment the counter. Now, we only run this for 10 clock cycles, but if we go back to the test bench and run it for, let's see. So we have the clock period is 10 nanoseconds. So if we run it for 2600 nanoseconds, we should actually see this counter wrap. So we can just do reload, zoom out, and well, now it's hard to read, but we can actually change this format into, let's see, it's analog step. And let me make it bigger. Okay, so now we can see that when the counter reaches 255, let me also add it as decimal. Here, the value of the count variable is 255, and then on the next clock edge, it will go to 0. Because we haven't instructed verilog, we haven't said what should happen when you reach the max value, which means that just it wraps around and starts again. So we can fix that. We can maybe add an overflow bit or an overflow signal like that, but I'm not going to do that now. What I'd like to show is what do you do after you have your verilog. So now we have our verilog design. We have checked that it seems to work as we want it to. What we want to do now is actually make a circuit. We want to transform this into gates. That's called synthesis. And there is an open source synthesis tool called yosys. So the command is yosys. Let me exit that. To be able to run the synthesis, you can see on yosys demos. But basically what it does is you want to read in the verilog. We want to read in a demo library. So the demo library in this case will contain our gates. So it has a buffer, it has a NOT gate, an AND gate, an OR gate, and so on. D flip-flops, D flip-flop with set and reset. And that's So we read in that library, and then we tell yosys to figure out the hierarchy of the counter. We ask it to do some optimizations, and then we do a technology mapping to this. Well, actually, this is to an internal technology library in yosys. It'll do the synthesis, and then we can map the different structures. So first we map the flip-flops to what's in the demo library. Now, here you can see it points to a file called .lib. That is actually a Liberty file. And almost like JSON, but not quite. So this is a very common format, which is how we describe what the different cells do. For example, here you'll have the area, you'll have the pins, direction input output, and the function, A naught. And A times B, A plus B, and so on. When we map the D flip-flops, you can also map the logic cells, and then we can write a verilog netlist, which will be a synthesized netlist. You can also write a spice file. So I can open up the counter. Actually, let's run it. So make synth, and that will run the synthesis. If we look in our make file, then that's running just this yosys with this script, tickle script. If we then open up the counter.netlist.v, we will recognize that we have now a bunch of wires. We have the NOT gates, and we have NORs, NANDs, and D flip-flops. So let's see if counter.netlists, and if we grep the DFFSR, we see, actually, if we do VC.L, you can see we have 8 flip-flops, which makes sense. This is an 8-bit counter, so that seems correct. Probably done a pretty good job. So this is a pure sort of gate level description of our circuit. It is should be exactly the same as this verilog. So those two files should be equivalent. Now we can check that by running the simulation again with the same test bench. And the way we can do that is in a makefile, instead of running the counter file list, I now run a counter netlist file list. And in that netlist file list, I'll include the demo library, the verilog for that, the synthesized netlist, and the counter test bench. So this is the same test bench as before. So if we run make run netlist, we see that runs. If we jump to our waveform viewer, let's go to somewhere in the beginning and reload. Let me zoom in. Reload. We can see that it looks the same, but if I go inside test here, I'll now see all these wires. So for example, if I plot number 18, I don't know what that corresponds to, but we can see that changing here. Now, this demo library doesn't really have any timing information yet. But I can go into the demo library. And what I could do is I could add, for example, a delay to the inverter. For example, let's say I know that it's going to have a delay of 1 nanoseconds. Pretty long delay for an inverter. But anyway, I can run again, and if I now reload my netlist, I will see that the edge actually moved. So we can see that that edge moved by about 1 nanosecond. 95 to 96. If I continue to make this delay bigger, let's make it something bigger than the clock, 20 for example, and I run again and reload. And now we can see that the simulation X's out. Now it doesn't work anymore. Now it doesn't know what to do. So this is sort of a quick check to see that what you synthesized, it sort of works as you plan. You can check again to see that the synthesis has done the correct thing. When you're ready, you can then do the layout, because you could actually do the layout manually for this netlist here. It takes a bit of time maybe, but it's not that hard. And if you wanted to, you could also run spice simulations. So if you have a spice library for your library cells, this is a spice file that is the same thing. So this is our 8 flip-flops. It has then the structure to generate the +1. Right, now I see it also adds voltage sources everywhere, which is a bit weird, but I guess you'd have to read the documentation. And this is actually just connections. This is just connecting one net to another net, which I guess is fine. You can't really lay that out, but that's okay. Okay, so that was a quick introduction to Verilog with a counter. And if you wanted to check how that works, then you'll find it on dicex. Thanks.